Really quick,
There we go. So we'll just skip those two.
really quick, can you just show the, it's okay. If you already did them,
Oh, this one here?
because
So
I
this is
wanted
the
to
one
take a
we just
screenshot
did.
of it. Or I can just take a screenshot later if you're going to upload it.
Okay, this is the one we just did. And this is the previous one. Let me see. The previous one was 24. And this was the previous one, where this ended up being the answer right here. This is the work I would expect to see for a problem like this.
Okay.
And for 25, the work I would expect to see would be the following. I'd expect to see this, the conversion to kilograms. I'd expect to see this, the conversion to meters per second. And I'd expect to see this right here. So when you're not given the units that you really need, you're going to break it up into 3 problems. Or maybe 2 problems, because maybe you're given kilograms and you don't need to do this, but are you with me there?
Yep.
Okay, and so that one was 26. My sleeping habits have gotten really bad, so right now I'm wiped out.
Oh, sorry. Are we wiping you out? Sorry about that.
Well, I think maybe it may also be I got my second shot today.
Oh.
So they're giving educators shots right now, and they gave me my second today. And they say the second's worse than the first, but the first felt like I got punched in the arm, and that's it. Well, that's not bad.
No, I've heard people feeling a little bit more symptoms in that.
Yeah, more flu-y and things like that. So I'm kind of weary about tomorrow.
Just stay positive.
Well, to stay positive, I need a nap.
And rest, yeah.
Okay. So this right here deals with Schrodinger's atom. This problem right here. For Schrodinger's atom, to contrast it with Bohr's atom, so this is just a very short treatise on this. Bohr's atom, the electrons orbit the nucleus. The orbits are n equal 1, n equal 2, n equal 3, where 1 is the first orbit, 2 is the second orbit, 3 is the third orbit. And when you look at the nucleus and you look at these orbits, so here's the nucleus, here's n equal 1, here's n equal 2, here's n equal 3. So the bigger the n, the farther away the electron is from the nucleus. And to calculate the energy of an electron in an orbit, you use the energy of the electron is negative RHC over n squared, where R is the Rydberg constant, H is Planck's constant, and C is the speed of light. And n, in this case, if it's in the first orbit, would be 1 squared. For 2, it'd be 2 squared. There are some problems with Bohr's model. For instance, You see this electron and this nucleus? They're attracted to one another. So what should happen to those two things if they're attracted to one another? The answer is they should come together, but they don't. So why don't they come together? That's a great question. They should. Secondly is, why does the electron have to be in the first orbit or the second or the third or the fourth? Why can't it be in between these two orbits? With Bohr's atom, that's not a possibility. He said that it has to be in one of these orbits, and that's it. So what's the reason? And the answer is, he doesn't have a reason. What else can we say about Bohr's atom? I always thought that when you look at Bohr's atom, if these guys are orbiting the nucleus, that's kind of like planets orbiting the sun, right? When you look at the solar system, what should you notice about it when you look at the planets orbiting the sun? And the answer is really simple. It's flat as a pancake. All of the planets orbit in the same plane, except Pluto's a little bit off. And Pluto's not even a planet anymore. Or maybe it is again, I don't know. I'll let the astronomers argue about that. So I think one of the problems with Bohr's atom is it's a flat atom. And I don't think we think of atoms as being flat, do we? We think of them being as spherical. Mm-hmm. Okay, so these are some of the things about Bohr's atom that you want to know. And when you look at Schrodinger's atom, and when I say Schrodinger's atom, it's his model of the hydrogen atom, just like Bohr's is the model of the hydrogen atom. He says, well, you know what? The electrons are waves. So this is kind of a novel idea. We learned earlier that you can treat light as if it were a wave, or light as if it were a photon, which sounds kind of like a particle. So if you can treat light as a wave or particle-like, then maybe you can treat particles like electrons as particles or as waves. So Schrodinger says, we're going to say the electrons are waves. Furthermore, they're standing waves. So the way to think about this is, here's your proton and this is your electron. So this is a standing wave. And this wave here is supposed to look kind of like this. Imagine this is a guitar string that's vibrating. So it vibrates, and what happens here is that the places where I have these little dots, the string doesn't appear to move, but when this vibrates, this little hill will go down, this little hill will go up, this little hill will go down, and it vibrates. And that's what gives you the sound, okay? And these are called standing waves because the wave doesn't appear to be moving from one place to another. Whereas if you take a person and they have a jump rope, and here the rope is attached to the wall, they can flip the rope, and what happens to this little part that they flip up? It seems to move all the way to the wall. Are you with me there?
Yeah.
So this is a moving wave, and these are standing waves because the wave doesn't move forward. So he said that, you know what, electrons are standing waves. And to get the energy of the electron, we use something called the wave function. So in algebra, they may have introduced this idea to you, a function, and they give you something like g sub x or h of x or f of x. Very commonly, they use this as a function, f of x, for the function of x. Were you introduced to that at all in algebra?
Yeah.
Okay. So that's a function. So there's a wave function that can be used to describe this wave. Now, instead of f of x, they use the Greek letter psi. So psi is the wave function. And you know how Cartesian coordinates like this, where you have x, y, and z, your function is actually based on x, y, and z. Okay. Whereas we're kind of used to just two dimensions where you have y and x. And so you say y equals mx plus b. And so our function is really two variables. But when you have Cartesian coordinates, you have three variables. Well, for psi, we have three variables. They are n, l, and m sub l. Now, because these are standing waves, you can only have certain values for n, certain values for l, and certain values for m sub l. And the way to think about this is that the n in Schrodinger's equation is a lot like the orbit in Bohr's atom, only it's called a shell. So here, let's look at n, a real quick treatise on n. N is called the principal quantum number. So here I'm going to put Qn for quantum number. There we go. L is called the angular momentum. Quantum number. And m sub l is called the magnetic quantum number. So for our wave functions, the values that n can be are 1, 2, 3, all the way up to essentially 7. The angular momentum quantum number that is allowed depends on what n is. So L can be 0 all the way up to n minus 1. So let's talk about this one before we go on to the magnetic quantum number. So if n is equal to 1, L can be 0 all the way up to n minus 1. Well, what is n minus 1 in this case? It's 1 minus 1, which is 0. That means L can be 0, but it can't be 1 because n minus 1 is 0. Now, if n is equal to 2, what can L be equal to? Well, it can certainly be 0 all the way up to n minus 1. In this case, it'd be 2 minus 1. So L can be a 0 or a 1. And for 3, you can have a 0, a 1, or a 2. This number here is always 1 less than the shell number. So the n is called the shell rather than the orbit. And so 4, you're going to have 0, 1, 2, 3. 5 is going to be 0, 1, 2, 3. 6 is 0, 1, 2, and 7 is a 0, 1. Now, technically, 6 could be 0, 1, 2, 3, 4, or 5. The reason it's not 3, 4, or 5 is because we don't have atoms that need those angular momentum quantum numbers. Now, the magnetic quantum number, m sub l, can be equal to negative L all the way up to positive L. So if we look at this third shell here, and we look at these quantum numbers of 0, 1, and 2, here, m sub l can be negative L all the way up to positive L. Well, negative 0 to positive 0, which means only 0. Okay? But here, when we're talking negative L to positive L, it could be negative 1, or 0, or positive 1. So what are the possibilities here for m sub L?
-2 to 2.
Right, so -2 or -1 or 0 or +1 or +2. Now, furthermore, for these quantum numbers, N is called the shell, L is called the subshell, and m sub L is basically the orientation of an orbital. And L also, not only does it give you the subshell, but it gives you the orbital type. So I know I'm going through this pretty fast, but this is some very confusing stuff. So you want to watch the other videos that where I've talked about this also.
Yeah.
So here, for the subshell giving the orbital type, something you need to remember that if L is 0 or 1 or 2 or 3, we actually give these designations. Instead of 0, 1, 2, and 3, we give the letter designation to S, P, D, F. And you need to remember that. And 0 is S, 1 is a P, 2 is a D, and 3 is an F. So in your 0 subshell, you have S orbitals. In your P subshell, you have P orbitals. In your D subshell, your L equal 2 subshells, you have D orbitals, and then you have F orbitals here. And you need to remember that order, SPDF, with some mnemonic or something like that. And you can make one up yourself. Some people do fine when they try to make up these mnemonics, and some people suck. The way I remember it is that some people do fine. So that's why I said some people do fine. Okay, so
it actually flows pretty well, so it's just SPDF.
It does, but it's not in alphabetical order or anything, you know.
No.
You could almost think of it about like sunscreen or something, right? Isn't sunscreen have like an SP?
Yeah, like SPF.
SPF?
It's SPF, but you can just add the D, SP.
Yeah, you can add the SPDF. Okay, a little bit more about the stuff. So when we look at the energy, so this is potential energy, and at top is high potential energy and low is low potential energy. The shells look like this. So if you have an electron in the first shell, it has less potential energy than an electron in the second shell. Are you with me there? Okay, so that's for the shell. When you look at the subshells, a 0 is actually, I'm going to change this. I'm going to do this, stability. And I'm going to have an arrow going down. So what's more stable, 1, 2, or 3? And the answer is the arrow points to more. So more stable is down. And that kind of makes sense, right? If you have more potential energy, you're going to be less stable. And if you have less potential energy, you're more stable.
So like radioactive energy.
You can, well, we don't need to even go to radioactive energy. We can just talk about book. Is the book more stable when it's on the ground or when it's on a table?
On the ground.
Well, if it's on the ground, it can't fall anywhere, right? So not much potential energy. You don't have to worry about getting hit by that book. But if you put it on a table and you're underneath that table, that book may end up hitting you in the head. So it's got more potential being on the table. Okay, when we talk about the, so this is the N energies. Actually, let's put lowercase n. When we look at the L energies, 0 is more stable than 1, is more stable than 2, is more stable than 3, which means an S is more stable than a P is more stable than a D is more stable than an F. And the M sub L's you don't need to worry about. They're all the same. All right, so we have enough information where we can attempt to answer some of these things. So here's the things that we want to be able to know about this 4, 2, -1. So if n is equal to 4, that's called the fourth shell. If L is equal to 2, and so I'm going to draw a little thing over here that says SPDF. What number do I write first for an S? 0. 1, 2, 3. A lot of people make the mistake and they start with 1. But we start at 0. You always start counting at 0. You may not say it explicitly, but you start counting at 0. Like when you're against a wall and you take your first step, that's the first step, right?
Right.
But the wall is 0. That's where you start.
Right.
Okay, so for L equal 2, you can see that this is a D subshell. Are you with me there? Okay, and because it's a D subshell, that means that it is a D orbital. And this is the one thing that always makes sense, is the type of orbital is the type of subshell.
Okay.
Now, it turns out that there's 5 orbitals. So if we take a look at this, if n is equal to 4 and L is equal to 2, M sub L could be equal to -2, -1, 0, +1, or +2. So these are solutions to that Schrodinger's wave equation. You can have a 4, 2, -2, a 4, 2, -1, a 4, 2, 0, which should be popular in Humboldt County, right?
Yeah.
420 friendly.
Yeah.
You must not be in Humboldt County.
In Eureka.
Oh, you're in Eureka?
Yeah, I'm the best. I'm in the best city in Humboldt.
Okay.
Okay.
Then you should know about 420. They talk
Yeah.
about it all the time. And then there's 4, 2, +1, 4, 2. Each one of these is a D orbital. So this is a D orbital. 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 And this is a D orbital. And collectively, when you look at all of these and add them all up together, it's called a D subshell. And we can be even more specific. This is a 4D orbital. So what does 4D mean? It's in the fourth shell. So you might be thinking, wait, I've heard of 3D, but I don't know what this 4D is. Is 4D like when you take acid? No. 4D means fourth shell. You with me? So 4 tells you the shell, D tells you the subshell, N tells you the orbital type. So there are 5 orbitals in this D subshell. Okay, so the answer to our question here is, what type of orbital does this refer to? We would base it on L equal 2 means a D subshell, therefore a D orbital. And it says, give the orbital label, it would be a 4D, regardless of what M sub L is. It's a 4D orbital, okay? Now, how many orbitals occur in the N equal 5 electron shell? So here we have to do N equal 5. and we have to do our L's. So can L be 0 for n equal 5? And the answer is yes. What is allowed for m sub L when L is equal to 0? Well, it can go from negative L all the way to positive L, so 0. So this is what you would call an s orbital because L is equal to 0. Now, we're still in the fifth shell, and we're going to let L equal 1. What can m sub L be? Well, it can be negative 1, it can be 0, or it can be plus 1. So what type of subshell is it when L is equal to 1? It's a p subshell. So this is a p orbital, this is a p orbital, and this is a p orbital. I don't want to write the whole word orbital out. And then can you have a 2 for L? The answer is absolutely. And you can have a negative 2, a 5, 2, negative 1, 5, 2, 0, 5, 2, positive 1, 5, 2, positive 2. And these are all d orbitals.
Yeah.
Now, it's kind of unfortunate that they picked this one here because we got a lot more work to do.
Yeah, that's what I was gonna say. I was like, this can go all the way down to like, what is it, 4? Like,
it can actually go, yeah, to 4. So here you can have a 5, 3, negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. And each of these are f orbitals. And there's 7 of them. And technically, you can have another subshell here. It's the L equal 4.
Yeah.
And you might be wondering, well, Tony, you never told us what a 4 is.
Yeah.
Well, I'm going to tell you now.
It's the time.
Are you ready? I like this. It starts going in alphabetical order.
Nice.
So yeah, thank goodness, right? So 4G, there's a 5H, there's an I, but honestly, there's never any electrons in those subshells. So that's why we don't talk about them. They exist in technically, but not in reality. Okay. So kind of like Santa Claus. Technically, Santa Claus exists because you talk about him all the time. But really, does he exist? No.
Well, maybe we just can't see him.
Oh, I didn't ruin Santa Claus for you all this time.
I know, this whole time.
Oh,
I just thought I couldn't see him.
I need to be careful. But the tooth fairy is real.
Oh, that's good.
Yeah.
I just haven't lost any teeth in a long time, so luckily.
Well, that's probably good. Okay, so here when we look at the 5, I'm going to do this for the 5. For L0, there's 1 orbital. For L is equal to 1, there's 3 orbitals. And to give you a sense of how to count 3, here we've got 0. So you see negative 1, 0, positive 1, 1, 2, 3.
Okay.
So with 2, you can have negative 2, negative 1, 0, plus 1, plus 2. How many orbitals is that?
You'd get 5.
That's right. And if you have a 5, 3, what are the values over here?
7, or negative 3, negative
Right.
2, negative 1, 0, 1, 2, 3.
That's right. So you got 7 orbitals. And what about for a 5, 4?
Would be 9.
9. And so you can see that the number of orbitals increases by 2,
Right.
because when you increase L by 1, you can have a positive and a negative of that.
Right.
So here, when we add the 2, you could have a -2 and a +2, which means instead of 3 orbitals, now you have 5.
Right.
So that's why they jump by 2.
Mm-hmm. You can just multiply the L by 2 and then add the 0, so it'd be like 2 more.
Yeah, you can multiply the L by 2 and
And then
add
add a
1.
1. Yeah. Mm-hmm.
Yeah. In fact, that's a formula for the number of orbitals. The number of orbitals is 2L plus 1.
Right, exactly.
I think the book may even give you that formula. But, it's just easier for me to say, oh, I can have all of these and I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here, how many orbitals occur in the 5th electron shell? We add them all up together. 1 plus 3 plus 5 plus 7 plus 9. 1, 3, 5, 7, 9.
24?
Pardon me?
Oh, is it 24?
I don't know. It's
9
5.
plus 7.
You know how I'm getting 25?
Oh, did I miss one?
What's 1 plus 9?
10.
What's 3 plus 7?
10. Oh, look, yeah.
Plus 5.
I was off by 1.
So see,
That
this
was
is,
faster. That was
yeah,
much
this
more
is,
effective than what I was doing. I was just adding 1 plus 3 and then plus 5.
see, these are what math nerds do.
Yeah,
It's
you find the
rather than do this in
complementary.
order, we just say, oh, let's do it the easy way. Let's find tens.
Yeah, yeah. You find the complementary number.
Yeah, find tens and then go from there. Okay, what are the letter labels of the subshells? So here, the letter is going to be for 0. What is it? S, P, D, F, and then G.
Mm-hmm. So all you have to memorize is SPDF. Then from there you just go alphabetically.
Right, and there you're going to have to learn the order of the letters in the alphabet.
That's gonna be the hardest part for me.
Oh, do you remember when you were in first grade and you asked, Mr. Lemon, am I going to have to know the order of these letters later, or can I just forget about it? And he said, no, 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 no. You do need to know the order because you're going to take a chemistry class someday where you're going to need to know the order.
I still have to in order to find. I still have to basically say them in order to really know them.
I know what you mean. I'm good to F. On there, I'm kind of like, I don't know what comes first, K or L or,
Yeah.
I kind of get lost there. I'm kind of okay with S and R.
Mm-hmm.
R comes before S. I get that one. And Z, of course, who doesn't know Z? But yeah, for me, I have to say the alphabet when it starts getting past F.
Yeah.
And I know it looks stupid when
You have to start singing the song again from kindergarten.
That's right. A, B, C, D, E. Okay, so that's number 28. I have time for one more and then I've got a jet.
Sounds good.
Okay, a possible excited state for the H atom is an electron in a 5D orbital. List all possible sets of quantum numbers for this. So it's a 5D orbital. What can we say about N? It's 5.
Yeah. Okay. Yeah.
It's that straightforward. What about L?
It's 5D. So D. What is it? SPD 3.
0, 1, 2.
Oh,
So
0. Oh. I did it. I
Cardinal
did the thing you
error.
told us not to do.
You started at 1. So this is
Yeah.
the wall. The wall is 0.
Gosh, 0.
Okay, so what is L equal to?
Zeros are important.
They are. Zeros are
2.
heroes.
2.
2.
Yeah.
Now, what are the possibility for M sub L?
There's negative 2, -1, 0, 1, 2.
Okay, so I'm writing them all out, each individually. Okay, so these are all of your 5D orbitals. And if it were a different question, if it were a 5p orbital, so this is for a 5p orbital, L would be 1, right?
Mm-hmm.
And M sub L would be -1, whoops, 0, and +1, right? This would be a px, this would be a py, and this would be a pz. And here's something else you want to know, that p orbitals look like this. That's a p orbital, where this is the Cartesian coordinates.
Okay.
So this is a px. What do you think a py looks like? Well, a py looks like this, where it goes up and down on the y. Do you see that?
Right.
And what does a pz look like? A pz looks like this, where it's on the z-axis. And when you put these three together, because this little dot here is the nucleus, the same nucleus for each. When you put all three together, this is what you get. And it basically looks like a sphere. So all subshells look like spheres because the orbitals that make them up, when you put them together, they look like a sphere.
Mm. Mm.
So the shapes of the orbitals that you should know is, you should know what an s orbital looks like. It's a sphere.
Mm-hmm.
The p orbital looks like kind of an infinity sign, but it's got 3 dimensions.
Mm-hmm.
Okay.
Okay.
All right. Well, this will get posted later today. I've got to run somewhere right now. Thanks for calling in. It's always nice when someone does.
All right. Thank you so much for your help, Tony. And I hope that you get a chance to rest.
Yeah. Well, I just hope that I don't get fluey from this dumb shot. I mean, this important shot, but you know what I mean.
Yeah, I know it's hard,
Yeah.
but
We'll
you
see.
got this.
Yeah, I got this. At least now, if I get COVID, I won't die.
I know there's a big difference between getting COVID and getting serious health complications and having like a vaccine, having like the flu for a couple of days.
Right. Well, they say that this will not prevent me from getting COVID, but it'll prevent me from dying from COVID.
Yeah.
I guess shots are really close to being 100% effective against you dying. You may end up in the hospital, but the vast majority of people are not dying once they get the vaccine.
That's good. That's good to hear.
Yeah.
Yeah, hopefully we all get it soon.
Yeah, we're kind of used to the idea that, oh, the vaccine means you won't get it.
Right.
Now I think we're trying to change the frame of mind for the COVID vaccine, is that, oh, you may get it, but you won't die. And all of a sudden, it seems like, wow, this vaccine seems a little bit more important than the flu. Because usually when you get the flu, you don't die.
No, yeah, it's totally different. And they always come up with new flu strains. There's always new flu strains as well. So it's like, now we're gonna have to be getting like multiple vaccines, I guess, yearly, possibly.
I think so. I think it's going to be like the flu, where they're going to have the chosen COVID vaccine every year, or maybe twice a year.
Yeah, I mean, it's better than like getting COVID. I've just heard so many stories. Like I work as a call agent for like a health startup kind of thing, and I get to talk to people from all over the country, and basically like I hear a lot of bad stories about COVID, so it really shouldn't be taken seriously.
Yeah. I, knock on wood, don't know of anyone who's had COVID.
Yeah, I mean here we're pretty isolated, but in other parts of like the country, yeah, it's pretty crazy.
Yeah, it is definitely crazy. So
Well, take care, Tony.
you too, and maybe we'll see you tomorrow. I'm going to be zooming at 10 and at 1:15.
All right, is that when you get the most people calling in? Or...
On average, I get 0 people calling in.
oh.
So this is a big day right now because I got someone who called in around noon, and you called in now.
Yeah.
So this has been a really busy day for me, and that's why
I've been trying to call in the mornings before work, but sometimes like I get caught up in the morning. But yeah, I need to do a better job of staying on track. I think like calling in is better because you stay on track, versus like having to catch up, which is like
we did
really crazy.
Yeah, we did have the choice of requiring students to come to class, but we were encouraged to not do that so that students could have their work schedule. But it's a double-edged sword.
It is like, it really is like, as a student, I think that like staying on track is definitely better than trying to catch up. And you mention that all the time, but I feel like it happens.
I think I have said that before. It's better to keep up than to catch up.
Yeah, so we'll see. After this week, I tried to catch up a little bit, so we'll see, hopefully.
Someone needs to do? Someone needs to invent a sauce that's called Keep Up. And then the motto could be, keep up is better than catch up.
That's true.
Some really nice sauce for French fries or something. Like a, fry sauce or whatever they call it.
Yeah.
Because keep up is better than catch up.
I know, Tony. We're trying to hear you out. We're trying.
All right.
All right. Have a good evening. Take care.
You have a good evening too.
Bye.